Hello everyone, this is going to be a video about how to do inverse kinematics inside IsaacSim. There are lots of different ways to do inverse kinematics. There's some built-in ways in IsaacSim, and there's lots of libraries out there that enable you to do it. This video will be going over one approach to integrate one library with IsaacSim. This scene here, we are testing the reachability of all of these different positions in our scene, and reachability is defined as we can get an IK solution within a tolerance of what we're aiming for. And you can see here, these are all places where we can get valid IK solutions, and these red ones, this are where we can't. I'm going to go over the details of the IK solving that we do for this project. So over here in VS Code, we set up this with two processes. We have a server, which we can call to allow us to do IK, and we have a client and simulation app, which runs IsaacSim. The reason we have it set up this way is because IsaacSim is in uses a bit of an older version of Python. We can have a look at what exact version that is right now. So that's down on 3.10, and it has a bunch of internal requirements, like it requires a certain version of NumPy and some other libraries that I would like to not mess with because I've broken various IsaacSim environments by installing external dependencies that will then change the NumPy version and things like that. And certain things in IsaacSim just stop working. So I prefer not to install big dependencies inside IsaacSim if they're not already in there. And so one thing that I use that for is that I don't want to install in there is this library that I use called PyRoki, as well as Jax, because that will definitely change the NumPy version and break it. So I run it in an external process, and we access it over just HTTP requests. If you want more performance, you can use other transport mechanisms, but for my purposes, HTTP requests are just fine, and we do them all in batch at the start before the visualization starts, so it doesn't slow anything down when we're actually viewing the simulation. So this is a HTTP server that we can call with our normal Python requests library. We'll go over the client first, but we can keep the server on the side for reference. So we have a basic client here. It allows us to do forward kinematics, inverse kinematics, and then batched versions of those. And then, as you'd expect, it uses the request library in Python, so nothing special here. It just calls that. It sets some JSON data with our joint values. We've got our pose matrices here. We do super simple serialization, just a JSON, and then our matrices are going to be turned into lists of lists. So nothing fancy on the serialization side. It means both sides can be super easy. They don't need to share like protobuf definitions or anything like that, although you can set it up if that's what you'd like to communicate like that. So we can call these here, and then they're implemented super simply on the other side. We're using Fast API, which is a super simple way to set up a HTTP server, and we've got some simple definitions of our types because that works well with Fast API. So we can see here, like a pose request is a list of floats, so that's a 4x4 matrix, and then for that batch pose request, it's a list of floats. So it's like a n by 4x4 matrix. And there's not much that goes on in here, HTTP wise. It calls our planner methods, IK or batched IK, or our FK variations. Takes these in, turns these into Jax things, calls those functions, and then returns them as lists, which we can then cast into NumPy arrays on the other side. So communication-wise, there's not many lines of code at all. All of the details for IK happen inside this planner class here, which is defined here. And even then, like most of the stuff happens in this PyRoki beam helper class. We set up our UIDF file because we need to load this with the UIDF file, and that gets passed with the excellent yourdf.py library, and then that gets passed into PyRoki and constructed from that URDF. And then we create our PyRoki beam helper, and we set up some things with like JAX's JIT and VMAP to get automatic batching and JIT for speed. We're going to dig into PyRoki beam helper because that's where all the details are. This PyRoki beam helper, this does a beam search over the possible solution space for our IKs that we're trying to solve for. This was introduced, this beam search, and of course the rest of PyRoki is all talked about in the PyRoki paper, a modular toolkit for robot kinematic optimization. This is very well written, and it lays out the internal ideas of PyRoki, and you can go read all of the source code as well at github.com/chungmin99/PyRoki. It's very easily readable, and for anything that you want to do, you can usually adapt it out of the snippets here. You come to see what you want. You're like, oh, I want trajectory optimization. You can go look at this. You can see the things that they import, how they set up, for example, collisions, and actually solve the trajectory optimization. In here, you can see it's importing it from this PKS, which is the PyRoki snippets, where we can see here, and then we can look at trajopt and see how this is implemented. For example, the one we're working with though, it comes from, I extracted this a while ago, but it comes from Benchmark, I believe, IK Benchmark. And yeah, here we go. Yeah, here's the PyRoki beam helper that we're using our own modified version of it just to make it slightly easier to work with. And we've got some of our own custom costs in there. For example, we've got this rest cost for this situation here. We wanted to bias the solutions to have the robot not be upside down and that sort of thing. So that's the nice thing you can do with PyRoki is you can customize all of these costs. But essentially, PyRoki works by you set up these different cost functions. So here we've got a list of cost functions. So this cost function will, this is what actually makes the solution end up in the correct position and orientation, and it does it using an analytical Jacobian method. We also add a cost function for so that cost function will increase the further we are away from our target destination. We've got a limit cost, so this is going to penalize the robot if it tries to propose solutions that are outside of the valid limits. And this is our rest cost as well, which is going to penalize it for being far away from a reference pose. And you can see here, I've set the weight. You can set this as either a scalar or a array. And this is because I only want to penalize certain axes of movement. The first axis, I want the robot to be able to rotate to wherever it needs to rotate. So I'm not going to penalize that at all, and that's why the weight is 0. And this value doesn't matter because it's getting multiplied by 0. We really want the second axis, first axis, second axis to be somewhere around 0.34. Again, these are not that strong, and it is going to have to be other values. We're just biasing it towards being over here so we don't get flips of the robot. Whereas, if we put this as, for example, positive 0.34, the robot would give me solutions that were upside down a lot more of the time, and that's not what we're looking for. So this PK rest cost is super useful if you have an idea of what your solution should look like, then definitely impose this here. Otherwise, you can get things that are upside down, for example. So we make our list of factors. These are all the things that we want to minimize. So we want to minimize the error of the final location. We want to minimize the exceeding joint limits, and we want to minimize how far it is away from a reference position. So now that we've got these together, we can create a JAX least squares problem. So this comes from the JAX least squares library. We give it the factors, we give it our joint variables, and we can analyze that and solve it. So this will compile this all into a nice big function. set up all of our configuration and use the trust region. And that is like a nice function to like solve one example of an IK problem. And then we can use VMAP and some other sophistication down here to solve multiple in parallel, find the most promising, and then zoom in on those and make them and optimize those ones even further. So and there's a lot of sophistication you can add on top of PyRoki, but this is the basic one. This is the basic approach that they talk about in the paper. So when they mention like beam search in here, they talk about IK beam. This is the approach that they're talking about. You can totally just use this solve one function as well, and you'll get good results. But these ones are much more refined. And so yeah, we call these IK functions through here, and we return those, and that's how you can do IK. That's one approach for doing IK inside Isaac Sim. Thanks for watching.